Hello geniuses, my name is Tensoro and I would like to welcome you all to the first class of yours truly. Now, you may have a lot of questions already. Why is my microphone 2D? What is this cozy looking chair I'm sitting on? Or most importantly, are my yellow eyes contacts? Now, today is not the day I'll be answering these exciting questions, but instead I want to introduce you all to the world of AI. Now, when I say AI, what do you think? Heck, I know you thought of ChatGPT. But what about in 2021, when the craze hadn't started yet? It could have been a ton of things. Robots, GPS, the YouTube algorithm, shameless plug, please sub. But nowadays, when we say AI, we mostly talk about machine learning. And then when we say machine learning, we really just want to say neural networks, which is part of deep learning. And you can see that it's under this umbrella term of AI. So that's what I'll be introducing. Now, online, we can find a whole lot about theory on neural networks. One of my favorites is 3 Blue 1 Brown's neural network quiz. I'll link it in the description. But what I'll try and teach is the step-by-step implementation of the theory into code that you can play with. Of course, I will still go into some light theory of what the code does, but I've always been fascinated with how you can just play with these AI models and adjust the code to your preference. My goal is to have you guys intrigued and demystify this AI stuff. Now, what I will be using to make some simple AIs is all on a website called Kaggle. It's a great place to find datasets, which are just giant clumps of data, essential to creating these modern AIs. Kaggle also offers an accessible coding feature, which when you click into their code tab here, and then new notebook, you can start coding right away. By the way, this website is called kaggle.com and you can make an account for free and do this right away. Now, you may have heard that training AIs require you to have a ton of computational power, which is drawn in most cases from GPUs, graphics processing units. So basically, to easily train AI models, the beefier your GPU is, the faster it'll go. And we all like fast. However, I know everybody doesn't have the beefiest of GPUs, but you can really do this on a $20 Chromebook because Kaggle is nice enough to let us use their GPUs to run our code. A lot of AI or data-oriented coding tasks are done in a programming language called Python and in documents called Jupyter Notebooks, which is just Python but fancy. I will try to be as beginner friendly as possible, but a basic understanding of programming will really help. Now, I know all of you are itching to get coding, so let's dive right in. Here we can already see that there's a bit of code written for us. This is basically Kaggle being nice to us and giving us a head start. We can see that this code in this cell, which is basically this box right here, gives us 3 libraries: NumPy, Pandas, and OS. Now, libraries are just collections of code that we can readily access to make our life easier, and we'll probably use these. Now, after these 3 libraries, Kaggle has given us these 3 lines of code. And basically what it does is it will print whatever files we have loaded into the notebook. Now, if I run this code right here, by pressing the run button here, we can see that it's running. Come on. Hello. Anyways, session started and it ran and it did absolutely nothing. Now, why? It's because we don't have any files. So what I want you to do right now is to go to the add input button here, search up MNIST, and add the MNIST and CSV dataset right here with the plus button. Now, if we go back, we can see that there is a dataset entered, an input. And when we run this cell here, we can see that there are 2 files. And when we click into this dataset, we can see that it has 2 files. So that's nice to know, and that we got an input up and running. Now, what is this dataset that you just added? You know when they say you should first learn how to walk before you can run? Well, the MNIST dataset is kind of that equivalent in machine learning, except instead of learning how to walk, MNIST is more like learning how to stand up. But no worries, I'll get you guys running in no time. So the goal is this. The data consists of hand-drawn numbers from 0 to 9, including labels for each hand-drawn image. So what we're going to do first is to visualize the first, we actually have to put our data into variables. To do this, we will use the MNIST read CSV function. We first are going to add another cell, and then we can say the training data is equal to, we use the MNIST read CSV function, and we are going to put the train CSV file path, we copy the file path here into the function as an input. And we will also, for the test data, we will do the exact same thing. Test data. And so now we have the two CSV files stored in the train data variable and the test data variable. And what this does is that it changes the CSV file into a pandas data frame object. And that's basically what the pandas library uses to store the data. You don't need to dive too deep into it. But here, if we print out the train data, sorry, I'm gonna run this cell first. I forgot it. Run this cell first. So we always need to run all the cells before it until we can get to the last cell. And that's kind of different than normal Python files, because in Python we can just run the whole thing, right? So this is easier because you can kind of separate the operations. So for the train data, we can see that the first column are labels. That basically means what the number is, like a literal 5, a literal 0, and all the other columns after that are basically pixel values in the image. And those would be the first pixel right here, all the way to the 784th pixel here. Now, if you recall, the dataset is actually just a collection of hand-drawn images, but all there is here are just some numbers. So where's the image, right? Well, if we draw this data out with the label being the first number, and then the rest of the numbers being pixel values, label the first number, which is this one right here, and the rest of the pixel values, which are these values here, we can see that it can actually be converted into a 28 by 28 image. Now, why is that? Because 28 squared is actually equal to 784 for the math whizzes who might have already found that out. So essentially what happens is that the first pixel actually goes into the top left-hand corner pixel, and then it keeps on going until the top right is the 28th pixel, and then jumps to the 29th here, and then keeps on going until the 56th pixel here. And it keeps on going until we get to the 784th pixel at the bottom right. So what we have to do right now is to change the 784 pixels into a 28 by 28 pixel image. And what I'm getting now here is still all of the rows here with this colon, but instead this time I'll need to get the first value for each of these rows using the 0 right here. Then convert it back into the NumPy array. And then here I'm going to use a type called an integer now. Now you guys might be wondering what these 32 means. Don't worry too much. It's just how many bytes is in one of them, or bits, sorry. It would be 32-bit float here and 32-bit integer here. You don't need to worry too much about it. Now, we've basically processed all of our training data, but now we need to process our test data. Now I'll explain the difference between the training and test data later, but first let's see what the test data looks like, right? It should look extremely similar to the train data here. Great. You see it's the same thing. We have all the labels and we also have all the pixel values. So we'll do the exact same thing, copy and paste, except we'll use test X and test Y and then the test data instead of the training data. There we go. We'll run that. And now we can get into reshaping our data. So if you recall, the shape of our data should be a 28 by 28 image. Now we've only made our 784 pixels and our labels into separate variables here. But what we really want to do now is to visualize the images, right? So let's reshape the training data first, which would be train X, which will now equal to train X dot reshape. We'll use this function into a shape of 28 by 28 pixels. We'll do the same for the test data. Now what these two lines do is it reshapes what something looks like here. I'll just show you guys what train X looks like. It should just be lines of just the pixel values exactly. So basically this row right here is essentially from here all the way across. So what we want to do now is to reshape it so that each row looks like an image. So now once we've done that, we can kind of try and see what each image is, right? So in this variable here, the first set of images, which we can get like this, we take the index of 0, we'll get the first image. And now this doesn't really look like an image, but we can use a library, plt, dot the function which is image_show, which it's image show, come on guys. Now before I forget, I also need to import the plt library. So what I need to do here is I need to import matplotlib.pyplot. Essentially what that will give us is the ability to actually run this line and show us the image. Now as you can see, the first image appears to be a 5, and we can verify that by going up to the training data and looking at the first label, which is indeed a 5. Now, just to make sure I'm not tripping, let's look at the second image, which is a 0. Now double checking, it is indeed a 0. So we know that we're doing something right. So now that we've seen what these images look like, I'll reiterate what we're trying to do here. What this model is trying to do is that we will give it an image such as this one, and it will basically tell us what number it is. So our model should just output a 0 when we give them this image, right? Now, for us, like, our eyes have been trained to, like, since our birth, but the model, well, we're gonna make it learn how to recognize numbers in, let's say, a few minutes, right? But you couldn't do that when you were a minute born. Anyways, I will also now introduce a data processing technique called normalization. Now, for this specific data set, it is not really needed, but it is good practice to essentially scale all the values you use for inputs into your model to a range from 0 to 1. So say, for example, since right now we have a data range from 0 to 255, but we want to scale it into a scale from 0 all the way to 1, so that this 0 here corresponds to this 0 here, and 255 corresponds to 1. Now, say let's have a random number like 200 somewhere in here. What would that scale into? That would be 200 divided by 255, which gives us 0.78, something around there, which would fit in somewhere right about here. So how we will normalize all of our data here is essentially to have our train equal to itself divided by 255. And we will do the same thing for the test data. Now, why we use normalization normally is because some data is normally overrepresented in models, but since each image in this data set is already in the same scale from 0 to 255, it's not really needed, but I'll do it anyway since it's good practice. So we have the images, but you may remember about our label data. What happened to those? Now, this is a bit technical, but there is a process called one-hot encoding. You can skip this for this project if you want, since you can still train your model without it. But there are a few reasons that I like to do it, which I'll explain later. So, what is one-hot encoding? It is basically a way to convert labels into binary values. So here I've written something that explains it. I'd like to think pretty well, but see it for yourself. If you remember, our first label for our training data was a 5, right? A number 5, and our second was a 0. So essentially, we need to convert those into, like using a process called one-hot encoding. And it looks something like this. A 5 will be converted into a list that looks like this. So basically, each of these numbers are essentially binary values, and there are 10 of them, each corresponding to the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And you can see that our first value is a 5. So that means the fifth one from 0, 1, 2, 3, 4, 5, the fifth one is a 1. And that's how our model will know like which number is which, essentially. So let's do one more, I don't know, kind of practice with you guys. Let's convert the number 2 to 1 encode, right? What would that look like? Well, the first number would be a 0, right? Because that corresponds to a 0. Now the second number would still be a 0, right? Because it corresponds to a 1. The third would be a 1, since that corresponds to the 2. And it goes all the way until the 0 that corresponds to a 9. Now, why does it start from 0 all the way to 9? Well, that's because we have 10 types of numbers, right? From 0 to 9. That's what we're predicting. Say if we were predicting from a number from 0 to say 20, well then we would have 21 zeros and ones, right? This would be like 21 digits long. So the function we use to convert our labels into one-hot encode is called toCategorical. Now I'll take the test y and train y, since those are our labels. Y and y will be equal to TensorFlow. We also need to import the TensorFlow library. And it should be tf.keras. Now, essentially what this function is doing is it's calling the toCategorical function from like the TensorFlow in Keras utilities functions to convert our training labels into one-hot encoded labels. We'll do the same for our test labels. So now we have essentially finished processing all our data. And for our next video, we will finally get on to making our AI model and training it. So I'll see you then.